Welcome to episode 1 of quantum mechanics, the wave function. Here are some of the topics that we're going to cover in this video. Firstly, wave-particle duality of matter. Secondly, the wave function. And thirdly, normalization and probabilities of the wave function. A few prerequisites for this episode are knowledge of basic calculus and integration, and also the idea of probabilities. Imagine a particle in your mind. It usually looks something like this. Now, what if I told you that this is an equally valid interpretation of a particle? Although this sort of a duality doesn't make sense at first, without this correlation between particles and waves, the entire theory of quantum mechanics breaks down. And it's all thanks to one simple relation, the Einstein-de-Broigle relation. Let's look into it a bit more. In the relation, h represents Planck's constant, p represents the momentum of our particle, and lambda represents the wavelength of the particle. This relation between momentum, which is a property of, particles, and wavelength, which is a property of waves, is what sets up the entire scene for quantum mechanics. The wave function, represented by the Greek letter psi, is a function in both space and in time. It's also a complex function, meaning it contains the imaginary number I, or root over -1. And it's also a mathematical description of an isolated quantum system, by definition. And all wave functions must compulsorily be solutions to the Schrödinger equation. Let's consider this wave function, which is confined between 0 and a on the x-axis. We notice that it's a complex wave function because of the I present in the exponent. Additionally, it's also dependent on both time and space. But what about this factor of root over 2 divided by a over here? Let's ask the question, how could we represent a wave function on a graph, or rather a complex wave function on a graph? One such answer of representing it is taking the modulus squared of the wave function. If you have a complex number z, which is of the form a plus bi, the complex conjugate is of the form a minus bi. And multiplying these two numbers together, we get a real number, which is the modulus squared. And we can represent this on the number line. Since the modulus square of the wave function is real, it can be represented on a graph. Let's take the following example. On graphing, we find this, where a squared is the amplitude of the wave function. Now, what is the probability of finding a particle in an interval dx? Well, this is dx. This is the modulus square of the wave function. And by a postulate of quantum mechanics, which is known as Born's postulate, the probability of finding the particle in this interval is the modulus square of the wave function multiplied by dx, and this is nothing but the area under the curve. Now, by analogy, let's see, if we take the integral, then we get the probability of finding the particle in an interval between a to b. And by setting the boundary conditions to -infinity and +infinity, we find that the particle's probability should be equal to 1. This only makes sense, right? But for our example, it is divergent, meaning it goes to infinity. And this means that our example could not possibly represent an actual particle. But for our previous example, it answers our question. The factor is actually called a normalization, and it makes sure that the area under the curve is 1 at all times. Graphing it, Graphing this modulus squared as W, we find that the area under the curve is always 1. The area under the curve or the integral is the orange line. No matter what we do, say if we change the value of A or we change N, the area under the curve is always equal to 1. We say that the wave function of the particle is normalized.